everyone. Start our lecture. I hope this is visible. So in last class we were discussing about this multi-layer training, and I said that backpropagation algorithm is the key. It's the key bit for training the multi-layer perceptron or multi-layer networks. Now here the basic thing you will require is that activation function is differentiable, without which it is not possible to train the network. And our simple data learning rule we are going to use to train this network, multi-layer network. But when it comes to the hidden side or hidden layers, we have to modify this delta learning rule a little bit, and then we can use to train the network, complete network, very easily. Now before I go to that thing, I would like to revise very briefly what we have done in delta learning rule, or what we have done for derivation of delta learning rule. And the concept was the gradient of error. So gradient of a vector quantity, gradient of a scalar quantity, it gives you a vector. And we have taken one example of mountain of uh, height of the mountain. Say this is some x direction, this is some y direction, and on z axis suppose it's height. So I stand here, then I have two coordinate points, that is x and y, and corresponding height. So if I stand say here, and if I take gradient of this height, so you can join all these equi-height points, it will form a locus, like something like this. And if you stand here and take gradient of height with respect to this point, then it will point you towards the maximum height from this location. Where is the steepest say, path from this location? So if you stand somewhere here and take gradient, it will show you this side or this path. So if you stand here, then you will get this path. So always gradient of a scalar will point towards maxima of that scalar quantity. So we are interested in minima actually, not in maxima, because we want to minimize error, not maximize. For a given network, we want to minimize our error. So when I take gradient of error, it will return me a vector which is pointing towards maxima. So when I take negative gradient of error, I will get a vector which is in the opposite direction, which will point towards minimum. Okay, so that's why we are always interested in negative gradient of error. The same is the situation depicted here. So if I am standing here, if I take the gradient, it will give me this direction, but I want to travel in this direction. You can assume this like error surface, and you're standing suppose here. So what are the variables in your hand? In your hand, variables are say weights. Suppose I take this two variable case, say w1 is here and w2 is here. Then I can change my position by playing with these two variables. Okay, so W1 and W2 in this case are two variables that I can change so that I can change the error. Suppose I am standing here, then maybe this much is the error. Say if I climb like this, then error is keep on increasing. So when I take gradient at this position, gradient of error, then it will give me this direction. But if I take negative gradient, then I will get this direction. Since I want to minimize my cost, I will take negative gradient. Suppose I am standing here and take negative gradient, then I will be getting this kind of direction. So basic principle is go with negative gradient of error. Now for that thing we have defined error for single neuron. So this was error for single neuron, that is desired response minus output square. So it's a squared error. So we have used measure for error as difference between desired response and output square of that. Now since I want gradient of error, I want gradient of error with respect to weights. So this will be actually a partial differentiation with respect to weights. So if I have different weights, then I have to differentiate this error with respect to all those weights. So it will be again a vector. So if I follow that, this thing we have seen earlier, so I am just quickly showing you. I will land to this equation, which is the gradient of error with respect to weights of the neuron. So this is about single neuron, how you are training a single neuron. Now we will go with negative gradient of error. So I can multiply this here minus, so this will be plus. So change in weight we will do with a multiplication, a controlling, say, variable c or learning constant that we can give a name. So d minus o into f dash into x. So this will be my change in weight formula for single neuron. Okay. Now based on this, we will extend the concept to train multi-layer network. So yesterday I said that let us consider a two-layer network. So this is output layer, this is hidden layer, and this is input layer. So this is input, output, and this is hidden. So connection between input layer or input actually nodes to this hidden is through the weight. Say I can write here V J I. Here it will be V11. So it is this one and this one. So initially the first number is corresponding to the neuron number. So this is neuron number 1. So I will write here 1. What will be weight here? This will be weight V1 connected to, say, ith input node. So suppose this is the jth neuron, then this will be VJI. So this is connected to jth neuron from ith input. So like that we can give names, and there will be weight associated with each of this connection. Okay, so for every connection there is some weight associated. Similarly, there is weight associated with each of these connections in the uh, for the output layer neurons. Suppose this is the first neuron, then I will call this as W11, that is from first neuron to first input. Say this is say kth neuron, then this will be W small k small g, because I am talking about this connection. So can you think what will be this weight? This weight W is capital K connected to say capital J. So it will be W capital K to capital J. Okay, so it is, remember, it is always written in reverse order. That is, you will write first thing as neuron number, and the second position is talking about input number. Okay, now when I collect all these weights associated with each neuron, then the collection of these weights is called as weight matrix. So how do I write? Suppose I take weight matrix for say connections between hidden neurons to output neurons, then we will write all the weights associated with suppose this first neuron in first row. Okay, then for second neuron I will write in second row, like that. For small k neuron I will write in kth row, and so on up to last neuron. Same thing we will follow for P matrix. Say the weights associated here, they are written in the first position, first row, then second neuron from this hidden side in second position, and so on up to capital J. So this will be small j and then capital J. So this will be small k, this is capital K. Okay, so this is the basic structure. Then we have defined error for single neuron as d minus o square. Okay, so since there are many neurons here in the output, now we have to modify this definition little bit. So what we are going to do is we are going to define this as half into summation, say I equal to 1 to capital K. That means error for each neuron is added together. So this will be di minus oi. So this is a small change in the definition of error for multi-layer network. Now we will try to train this circuit using generalized delta learning rule. So generalized delta learning rule is for multi-layer networks. So we can start our thing uh, from the last layer. Why? Because we will apply input here. We will pass on this input to the first layer of neurons. We will calculate output for all these neurons here. So output is calculated, say here, for y1, y2 up to yj. That is passed on to next layer, and output is calculated. So output is calculated at the last layer, and then it is compared with corresponding desired responses. Okay, so we will use this error calculation to calculate overall error of this circuit. Okay, and that we are going to use to train these weights and later on these weights. So how we can do that? Let us see. So when I take output here, I know for during training what is corresponding desired response. As per our modified formula, we are going to calculate the error. So this one. Now, since we know that the controlling elements in our hand are weights, so weights are the important thing here to manipulate and reduce the error. So we will calculate negative gradient of error with respect to weights again. Okay. Now for the last layer, our weights are W, K, J in general. Suppose this is some kth neuron in any intermediate kth neuron. Then any weight I can call it as WKJ, which is connecting kth neuron to jth input. Okay, say this is WKJ. So this is a generalized, you can say weight, so that we can proceed our derivation. Now, when I differentiate error with respect to WKJ, so error is defined like this. So as such, there is no relation. You may not find a relation between, say, error and weight directly, because there is no W symbol here. So if I differentiate this with respect to WKJ, you may say, okay, since there is no WKJ involved, answer is 0. So that is not the case. We have to exploit the relation between, say, error and net. Okay, since net of this neuron is directly related to output. Okay, so output is f of net. It's a function of net. So I cannot say there is no relation between net and output. But you know that net is also dependent on, say, W transpose X, that is input. So now you can see there is a relation between, say, error and weight. So I can write this as error is equal to half summation k equal to 1 to capital K dk minus function of W transpose, suppose Y in this case, like this. Now if I take a partial differentiation with respect to WKG, then you see that there is a relation. Okay. Now to calculate this, I use chain rule. So what I can see is change in error with respect to change in net multiplied by change in net with respect to WKJ. So if I apply the chain rule, then I call this, say, change in error with respect to net K as some delta signal. Okay, this is some delta. Now you will see importance of this delta in next step. So let us define. So this is symbol for define. So delta OK is defined as negative of change in error with respect to change in net K. Okay. Now, if I use this symbol in above equation, say equation 1, then I can write, or I can replace here this by negative delta OK. So this becomes now equation 2. Now, if I take out this second term and try to do the partial differentiation, I know that net K, say net K is W transpose, say W transpose Y. Okay, that is input vector. So W, actually I should write W for kth neuron. I can take that particular row of that W matrix. So if I take WKJ differentiation with respect to this WKJ single weight, so I have to remember, I have to do this for each and every connection to find out this delta signal. So if I differentiate with respect to WKJ, so all these terms are getting vanished, and only term related to W small kj will remain, and somewhere it is there, so it is WKJ multiplied by YJ small j. So if I differentiate with respect to WKJ, only YJ will be coming out. Now if I do this for all WKJs, that is J equal to 1 to capital J, if I differentiate with each of these weights and try to collect all of them, then it will be gradient signal. Okay, so that gradient is minus delta OK into Y, because this, when I differentiate with respect to WK1, I will get Y1. If I differentiate with respect to WK2, I will get Y2, and so on. For WK capital J, I will get YJ. So if I collect all this, then it becomes Y, that is input. So this Y is a vector, and this is my error signal delta OK. Now what is the value of delta OK? How to compute that? So again we have to use chain rule. So delta OK is defined as, from this we have already defined, which is equal to negative of change in error with respect to change in net K. Now there is a relation between net K and output. So as my net changes, output is also changing. So there is a link, actually you can see output is related to net and net is related to weight. I have written here that relation. You have to remember this for this derivation. So weight is related to net and net is related to output, or vice versa. Output is related to net and net is related to weight. So this fact we are going to use in chain rule. Now next step, we are calculating this quantity delta OK using chain rule, and now we are differentiating with respect to output. Now here I am just writing the definition of error for our multi-layer network that we have defined at the beginning. So this capital E is now replaced here, and differentiation is with respect to OK. So this is nothing but f dash of net k. What is OK? OK is output of kth neuron. So when you differentiate, suppose I clean this. So this is my output O. So if I differentiate this with respect to net k, this is output k differentiated with net k. So this will be differentiated with respect to net k, and this is nothing but f dash of net k. So I'm writing here as f dash of net k for this group, and this you can calculate from the error definition. Now when you partially differentiate, or you take this term inside, so you can see that I am differentiating with respect to OK, and k is ranging from 1 to capital K. So I can expand this actually. So you can see that thing if you want. So D, say do OK. So I can write this as half into D1 minus O1 square plus D2 minus O2 square plus and so on. It's D small k minus O small k whole square plus and so on. dk minus OK capital square. So this is expansion of this summation. Now when I differentiate with respect to small k, that is small OK, so only this term will remain in the output of this differentiation. All others will be 0. Okay. So you can see here the differentiation is 2 into minus half dk minus OK into f dash of net. Okay, I think there should be minus here, and this minus and this minus will get cancel out, so it will be plus. So finally I got this delta OK, and if I see that it is dk minus OK into f dash of net. So if I substitute this things, all these things into proper place, okay, so I will get gradient, and negative of that will give me change in weight. So this change in weight is equal to learning constant, that is some symbol eta or c, into dk minus OK into f dash of net k into yj. So this is weight change for a single connection. We have to do this for all the other connections. Okay, so we can do actually in one step when we go for say matrix multiplication. So we can do this very easily in one step. Thing is that what you obtain is simple delta learning rule that we know. So last layer is trained still by using delta learning rule. Okay, so there is no change. So since I know desired response for last layer, I know output of last layer, I can calculate f dash, I can solve everything for last layer. Now we will go to the hidden side. How do I train here? I can completely find out all these things using simple delta learning rule. Okay, simple this thing as usual. Now we will try to find out this. Principle is again change the weights to reduce the error, so that you will be again using uh, negative gradient of error. Thing is that you will now differentiate with respect to hidden weights. Now this is suppose some jth hidden unit. So associated weight for some ith input is Vji. Output is Yj, input is Xi. Now we are going to follow exactly same steps, not a single change. So initially we in earlier case we differentiated with respect to Wkj. Now we are differentiating with respect to Vji. So gradient of error with respect to now Vji is the partial differentiation of error with respect to Vji. Again use exactly this relation, same relation, that is weight, net and output. So use chain rule and say equation 1 is now changed to 2. That is initially we differentiate with respect to net and then we differentiate net with respect to Vji. So this is some intermediate term. So I can use intermediate term only if there is a relation between these two variables. Otherwise, we cannot use. Since Vji directly controls the net of this neuron, net j of this neuron, so I can use that. Now again we will define delta signal for hidden layer. So that is delta Yj now. Earlier we defined delta OK for last layer. Now I am going to define delta Yj again exactly in same fashion. So it is now partial differentiation of error with respect to net j. Earlier it was net k and negative of that. Okay, so this equation 2 we can rewrite as 3. So I'm just writing in place of this using this definition, right, like this. Okay, so you can keep this thing for next step. Now here this second term net j differentiated with respect to Vji. So net j is nothing but summation like this, that is all the inputs multiplied by corresponding weights added together will give you net j. So when you differentiate with respect to Vji, only the term intermediate term say associated with Vji will remain, that is Xi. So when you differentiate with respect to all Vji's, that is this weight and so on up to last weight, you will get a gradient vector like this. Okay, a gradient vector like this. So X is a input vector. Now again, how to find out delta Yj? So delta Yj you can compute using again chain rule. So earlier we use output as the intermediate variable. Same thing we are going to do here. So this delta yj definition, we know that from previous step. So replace that using intermediate variable output yj. Now here this error I am writing as it is, as per our definition of error, and that we have to now differentiate with respect to yj. The second term here is f dash of net j, that we can write directly as it is just differentiation of output with respect to net. And since yj is equal to function of net j, so if I differentiate this with respect to net j, this will be just f dash. Okay, so this is very simple. So I can write this like f dash of net j. The only thing is we need to calculate this partial differentiation. As such, you may not find relation between yj and this quantity, but there is a relation. What is that relation? So for that, I will substitute this OK output of the last kth, you can say, neuron as f of net k. Okay, so this is simple. Output of last any kth neuron is equal to f of net k. Now what is net k? So here comes the relation. Net k, you can write this as wk transpose y. Okay, wk transpose y. I'm just making the link. Now this wk transpose y and this is delta yj. So if I differentiate this, suppose equation number 4 with respect to delta j, then you can solve this as usual. You can take this 2 here. Okay, these terms will remain as it is. And multiplied by this term. Now if you simplify this further, you can see this group from this step, which was defined earlier as delta OK. Okay, and then I can write this as delta OK into weight W kj. So if I do like this, the change in weight for Vji is equal to learning constant into summation k equal to 1 to capital K delta OK Wkj into f dash of net j into xi. So this is how we can change the weight for hidden side. Okay, so I'm just rewriting here. This is the change in weight for all these neurons, for all these weights, and this equation we can use here. Now you can see this delta OK is calculated for each neuron in the output side. So this delta OK is used to change weights here. So all these deltas are these error signals calculated for the next step is used to change the weights for previous step. So this is a key thing. So here we are going to calculate delta y1, then delta yj, say delta y capital J. So all these deltas, if suppose there is one more layer, say like this here, then you will use these deltas and this same formula. So this is a key formula. So this delta OK, in that case, we are replacing by delta yj. And then we will update these weights if they are there. So key thing you remember is, we will take one example, don't worry about that. Suppose this is the situation, this is output layer. So we will use some delta O signal, say this is delta Y and suppose this is delta L, suppose. Say delta O is used to change, say, weights here for this hidden layer. Delta Y is used for this layer, this weight updation. Delta L may be used for previous layer. So like that. So this error signal is traveling in reverse direction. So that's why it is called as error backpropagation. Okay. Since error is traveling in reverse direction, it is called as error backpropagation. So we'll stop here. We will see example in next class.